So in the last class we talked about bending stresses, and we derived a formula to calculate bending stress at different points in a beam if a particular value of moment is applied on that section. And I hope you remember this derivation, and we'll now write a more useful, commonly used variant of this formula, so that it will be very easy for you to remember this and use it to solve problems. So if you see here, sorry about that. So if you see here, from here we have found out that the value of stress, bending stress at a distance y from the neutral axis will be m divided by I. I into y. So we can write sigma by y is equal to m by I, and we also know that sigma by y is also equal to E by R, or E multiplied by K. K is nothing but the curvature. So curvature is equal to 1 by radius of curvature. So K can be written as 1 by R. So sigma by y is equal to E by R, and that is also is equal to m by I. So this is this is an equation that you are going to see quite often. Just wait, what happened? It's all right. So the equation we have derived can be written in this way, so that it is very useful for you to apply this to problems. So sigma x by y is equal to m by I is equal to E by R. So what are each of these quantities? Y is the vertical distance from the neutral axis, sigma x is the bending stress, m is the moment at the particular section we are considering, and I is the area moment of inertia about the neutral axis of the cross section, and E is the Young's modulus of the material of beam, and R is the radius of curvature. So this particular formula is often quite useful in solving problems. I think in the last problem I've given you had used the same formula, but in the format we derived. So there can be I think a lot of problems are available in textbook, so I'll give you a couple of them as a part of your assignment, and I would like to I want you to have a look at these problems and understand how we actually solve them. So I think so the one we have solved is a very basic one, where you can directly apply the equation and get the answer. So I have given you an assignment in your assignment questions in your group, which you can access and submit later. So I'll just okay, it's not here. I'll just discuss them so that you get an idea about how to deal with these problems. Why is this? Okay. No. Yeah, so this is the question you need to solve. Put it here. And you need to write your personal details here, and I have 4 problems here. What is the first one? First and second problems are basically, I think this is shear stress, right? Capacity is maximum elastic stress. Compression. So this is shear stress. Okay, there is one question. Okay, yeah, fine. Let's see the first problem here. So the first and second problems are from the bending stress section, and third and fourth problems are from shear stress, shear flow section. So 1 and 2 can already be solved using what we have already studied so far. So here we have a small steel T-beam which is used in an inverted position to span 400 millimeters. And if due to the application of 3 forces shown in the figure, the longitudinal gauge at A registers a compressive strain of a given value. And now the question is, how large are the applied forces if value of Young's modulus is 200 GPa. Now how do we address this problem? Now if the value of compressive strain is given, you can calculate the put it in your Yeah, so this is the problem. Now they are saying that the longitudinal gauge at A registers a compressive strain of this value. So where is the gauge positioned? It's at A. So this is the cross section of this particular beam. And A is this part here. So we are taking a section here, and this is shown here. And gauge A, this gauge A is essentially it's here. Now that registers a compressive strain of this value. Now you know that from Hooke's law, stress by strain is equal to E. That means that stress is Young's modulus multiplied by strain. So you will get the value of stress at that point from the compressive strain. So if the strain is compressive, you can guess what kind of stress will it be. The magnitude will be obtained from Hooke's law. So once you have the value of sigma, how do you proceed? So I told you that this particular formula is quite useful. Now let's see sigma by y is equal to m divided by I. Let's see if this part will help us. Now beam section is here. If you have the beam section, you can calculate the position of neutral axis. Find the position of neutral axis. How do you find out the position of neutral axis? If you have the cross-sectional area, it is essentially the centroid of the area. Why is it the centroid of the area? I think I've given you justification and derivation regarding that, which you can refer. So here we have done a derivation, and we have actually proved that neutral axis is at the centroid of the given cross-sectional area. So you can find out the centroid of the cross-sectional area. Procedurally you can, okay, so procedurally what you need to do is you just split this area into two parts, split it into A1 and A2. This can be cut into two parts, A1 and A2. And you know now centroid of A1 and A2 is nothing but the exact geometrical center of that part, and using x1 and x2 may be considered the distance to centroid of each of this area. And once you have that, you can use the equation for calculating the centroid. So once you have figured out the neutral axis, let's assume that the neutral axis is here. Depending on the dimension, it can be somewhere up or down. So I have not calculated, you are supposed to do that. Let's assume that it's here. Okay, this is neutral axis. Now distance from this neutral axis to gauge A is y. This distance is y. Yes, so where are we? Right. So we can calculate stress from strain and material property, which is sigma here, and y is nothing but the distance between the position where gauge is placed and neutral axis, which is y. And I is the, so we know this one, and I is the moment of inertia of the cross section about neutral axis. So you have two rectangles here. You can calculate the moment of inertia of these rectangles about its geometrical centroid using the regular formula BDQ by 12, and once you have them, you can calculate the moment of inertia of these areas about neutral axis, and then add them up. So there is a different formula that. So once you add them up, you will get total I. Now the next part is M. So now you have a sigma, y and I. The remaining part is M. M is the moment at this point. So what will be the moment at this point? How do you calculate it? Here you need to remember some lessons from engineering mechanics. So you have a beam here, and at three positions forces are applied, P, P and 3P. So how do you calculate the moment at this point? All these distances are given. So what you can do is first consider take your beam out, take the beam out and calculate draw the free body diagram of the beam. So this is a reaction force. Let's call these points A and B. So this is the reaction force at A, and this is the reaction force at B, and you have force P here, and 3P somewhere else, and this is the point of interest for us, A. So here you can find out this RA and RB, or just one of them, either RA or RB. That depends on the strategy you follow to find out the moment. I would personally calculate one of them. You can use equations like net force. Since this structure is not moving and it is in equilibrium, net force in y direction should be 0. That means that P plus 3P should be equal to RA plus RB. And you can take moment about any point. For example, you can take moment about this point. So P, that means that P multiplied by 100 plus again another P here, P multiplied by 200. That is the distance between line of action of P and the point about which we take moment, which is A. So P into 200 plus 3P multiplied by 300, 3P multiplied by 300, and they are all in clockwise direction. So you can take it as positive if you want. So if you take it as positive, then the moment due to RB should be negative. So I can take, or I can simply equate these two moments. So I can take RB multiplied by the total distance, which is 100, 200, 300, 400. So from these two equations, you can calculate you can calculate let's say RB as a function of P. All right, you will get the answer like something like 4P, 4.5P, 6P. So it will be a function of P. Function of P means the answer will be something like Kp or something. Now once you have Rb, you can find out the moment at this point. You can take out one of the section, and the moment about this point will be, which is our M, that will be 3P multiplied by this distance, that is 50 plus, not plus, minus. We just need the magnitude of M, so we don't need to worry about the direction, because we already know the direction, because all these forces are downward, and we know that this longitudinal, the compressive strain is there in the upper part, so stress will also be compressive, so we don't need to worry about the direction. So 3P multiplied by 50 minus RB, which you have calculated here, which is now Kp or something, so RB multiplied by 100 plus 50, 150. So this will be the value of M. So you will get the value of M as a function of P, and everything else we already know. Sigma we know, Y already know, I we already know, and M we know as a function of P. So P is the only unknown in the entire equation, and you can calculate P, and that is the question. What is the question? How large are the applied forces? So what are the applied forces? P, P and 3P. So once you have the value of P, you know how large are the forces. So the question is basically to calculate P. Now second question, determine elastic positive bending moment capacities around the horizontal axis for beams having the cross sections shown in the figures. The maximum elastic stress in tension for problem 6.9 in 10 KSI. What is KSI? KSI you can as a unit you can convert to SI unit, and in compression 15 KSI. The corresponding stresses for problem 6.10 are 100 MPa and 150 MPa. Okay. So what is the question here? The maximum elastic stress in tension for first problem is 10 KSI, and maximum elastic stress in compression is 15 KSI. And for 6.10, for this problem, maximum elastic stress in tension is 100 MPa, and maximum elastic stress in compression is 150 MPa. So these are the given data. From that you have to calculate the elastic positive bending moment capacities. How much bending moment can be applied in these two sections. So let's let me just put this figure in the board and talk about it. So this is the problem we have here, and just like the previous problem, we will probably need our simple equation, which is sigma by y is equal to m by I, and we are being asked to calculate the bending moment capacities. So it's just the value of bending moment you need to calculate. So m is equal to sigma I divided by y. And it's quite straightforward, but the only thing you need to consider is that they have given us the limiting value for both tension and compression, and you need to find out first the value of bending moment using limiting value of tension, and then calculate the bending moment using limiting value of compression, and from these two values of bending moment you will choose the smaller value, because you need to make sure that limiting values of stresses are not crossed. Okay, so first your job is to convert KSI into familiar units. It's essentially stress, so you can convert it to Pascal or something if you like, megapascal, whatever you like. Here also corresponding the units are different. Here so you have to convert both length and stress to corresponding SI unit. So I will not worry much about the units here. So to focus on the problem, your first I think the first job is to find out the neutral axis. How will you find out the neutral axis? Let's say this is neutral axis for first figure and this is the neutral axis for second figure. Here you can, in this problem you can divide this area into 4 parts if you like. Let's say I can take this area and divide it into 4 parts: A1, A2, A3 and A4, and I can calculate the moment of inertia of these areas about their corresponding centroid. After that, using the formula for finding the centroid of the collective centroid of the whole figure, I can find out the location of neutral axis. Once I have the location of neutral axis, I can add up all moment of inertia values about the neutral axis and get the total moment of inertia about neutral axis. Or I can take areas area A1 and A2. A1 is the bigger area and A2 is the smaller area. I can subtract A2 from A1 to get this area, right? The bigger area minus smaller area. So that's another approach. So using that approach also you can calculate the location of neutral axis. And then find out the moment of inertia. Here you had to add up all the corresponding moment of inertia about neutral axis. Here you have to subtract moment of inertia of A1 about neutral axis minus moment of inertia of A2 about neutral axis. Once you do the subtraction, you will get the I value about neutral axis. Similarly for this figure, you can, for this figure you can't do this approach. This approach is not useful here because it's very difficult to divide this area into really small parts. So the only approach that will work is this approach, the bigger area A1 minus smaller area A2. So using this approach you will find out the I for two different sections. Now for a positive bending moment, you will have compression at the top and tension in the bottom, right? So this is positive bending moment. You're basically trying to bend the beam. The uppermost layer will have one minute. So yeah, so where was I? M is equal to sigma I by y. We have calculated I for both of the sections. Yes, so for positive bending moment you will have you know that you have compressive stress at the top and tensile stress in the bottom. So for first problem you have tension 10 ksi here. Why did I put tension 10 ksi here? Because I know that according to this formula we assumed that bending stresses vary linearly from neutral axis to outermost point. So I know that maximum value of bending stress will be here, and it is given that maximum elastic stress in tension is 10 ksi. So the maximum value should appear here. So using the maximum value of 10 ksi sigma, I can calculate the bending moment value. So put sigma is equal to 10 after converting to proper units. Okay, use the value of I, and y will be what? Y will be the distance between neutral axis and this point. So using that you will calculate the value of m. Value of m for maximum elastic stress in tension. Okay, we will call it m1. Okay, and then calculate m2. How? For the same problem it's given that maximum elastic stress in compression is 15 ksi. So the compressive stress happens at the upper part of the neutral axis and the maximum value of compression happens here. So here you have value 15 ksi. So if you have 15 ksi there, put sigma is equal to 15 ksi. I is exactly the same as the previous problem, as the I is same for given cross section, right? You already know that. And y will be the distance between neutral axis and this point, uppermost point. Using that you calculate sigma I by y, which is m2. So you have two bending moments, m1 and m2. But which will be the bending moment capacity of the beam? That will be the smaller one of m1 and m2, because we need to make sure that the limits, the maximum stress does not exceed the given limit for both values 10 and 15. So we have to take the smaller value of bending moment. So the exact same approach can also be done for second problem. The exact same thing, calculate m1 sigma I by y by assuming that here you have 100 MPa maximum tensile stress, which will be here. Put 100 MPa, put sigma is equal to 100 MPa, put y is equal to distance between neutral axis and this point, find out m1, then the maximum compressive stress will happen here, that will be 150 MPa, and put sigma is equal to 150 MPa, calculate m2, and y will be the distance between neutral axis and this point. And once you have m1 and m2, calculate the lower value of m1 and m2. The lower value of m1 and m2 will give you the elastic positive bending moment capacity of this particular cross section here. So this is how you solve the problem. So now I have described you how to solve first two problems, problem 1 and problem 2. So you can start solving that. You can solve it and save it as a single PDF. Single PDF means first problem one PDF. In assignment, question number 1 should be single PDF here. Question number 2 should be single PDF here. And 3 and 4 are to solve 3 and 4. You also need the idea of shear stress, which I haven't covered so far. So I will cover it in the next lecture. So for the time being, this is already 36 minutes. I'll stop it here. I'll upload this video to YouTube, and you can refer it later also.